Okay, this is a quick review of Unit 5. Unit 5 was energy and matter flow and cycling in the biosphere. One of the main ideas was that in order for life to exist, it needs material and it needs energy. The energy has to come from somewhere. That somewhere is usually the sun. So usually the sun doesn't mean always the sun. Sometimes sulfur components, sulfides, are the source of that energy. If the energy comes from the sun, the process is photosynthesis, and this is one we're familiar with already. If it comes from sulfides, it is chemosynthesis. Photosynthesis is by far the most common, prevalent, important one. Without continual input, without constant resupply of energy from the sun, then there will not be enough energy to keep our ecosystems alive. We had some definitions. Autotroph are things that feed themselves. Photoautotrophs do that with light. Chemoautotrophs do that with sulfide compounds, with chemicals. Heterotrophs are things that eat other living things, as opposed to autotrophs, which make their own food. Herbivores eat, so vor means eat and herb means plant, and carnivores eat meat. This word type here is where I was testing if I could type things. Ignore. We have producers, consumers, and decomposers. Producers are things like, so things that are autotrophic, things like photosynthetic or chemosynthetic organisms, things like plants, algae, that sort of thing, cyanobacteria. Consumers can be primary, secondary, tertiary, quaternary. They are things that eat other living things. And decomposers break down dead material. So animals that are dead can be decomposed. Decomposers are frequently things like bacteria, fungi. So bacteria can be decomposers. Fungi can be decomposers. Lots of insects can be decomposers. I didn't mean to draw a circle there. I'll erase it. Well, it wasn't a circle anyway. Can be decomposers. And things like worms, grubs, etc. can be decomposers. They help to return inorganic nutrients back to the ecosystem, where they can be reabsorbed through the roots of plants. If we're looking at something like a food web, there might be, what do they do? We might look at something that has an arrow coming towards it and call it a consumer. We could count the number of arrows to figure out what level of consumer it is. So there's one arrow here, one arrow here, and these fish have no arrow showing where they, oh yes they do. They get their food from these guys, which get their food from here. So here are our producers, here are our primary consumers, here are our secondary consumers, tertiary, and then finally quaternary consumer. So if you want to find the level of something on a food web, you just need to count the arrows back until you reach a producer. At least one of these arrows on this picture is not in the correct direction, I'll tell you that. So which one receives the least amount of energy? This would be the one at the highest trophic level. So you would want something like a quaternary, so a fourth level, or a fifth level consumer would be something that receives the least amount of energy, and something that receives the most would be the producers. We looked at energy and matter flowing through ecosystems, and we described it using 3 different types of pyramids of energy, where only 10% of the energy is available for each level going up. The higher trophic levels, there are fewer of them, and as we go down lower and lower and lower trophic levels, so as we go down each trophic level, there has to be a lot more producers than there are primary consumers, than there are secondary consumers and tertiary consumers. there have to be about 10 times as much energy collected as for producers than is available for the secondary consumers, and so on down the line. That does not mean that our tertiary or quaternary consumers don't need a lot of energy. They still need lots of energy. But what it does mean is that there has to be so many producers to support them. Pyramids of energy show this because they're following that rule of 10%, where we are losing 90% of the level through each trophic level, energy through each trophic level. Pyramids of biomass are when we cut down and dry massive living or once living matter. Pyramids of numbers are where we count things. These ones could be upright in shape, we would say, with more producers and fewer primary, secondary, tertiary consumers. Or they might look weird. They might have a few things at one level, lots of things at another level, and other little lumps and bumps in there. And that's the case if one of those things is something that has a lot of mass. So like one big tree supporting lots of insects, which support fewer birds, etc. Or maybe we have lots of plankton, and they are supporting lots of krill, and that supports one whale, but that whale has lots of parasites living on it. So this shape is kind of a blobby shape like this. So that one whale is just one thing, but it's a lot of mass, which can feed a lot of parasites, for example. Our trophic levels are 1, 2, 3, 4, 5. Our first level is the producers, then our second level is the herbivores, then we have our secondary, tertiary, quaternary consumers. Herbivore is the same as primary consumer. If we have food webs, we might consider what happens when they change. If we have more producers, then we can feed more primary consumers, which can then mean we feed more secondary and tertiary consumers. So instead of our food web looking like this, if we do a pyramid of energy, if we have more producers, that just means that we can support more. So the width here, the length side to side, is going to be the number that we can fit in there. So more producers means that we can support more primary consumers, which will then support more secondary and more tertiary and quaternary consumers. Just the entire amount of life that's available goes up. For biogeochemical cycles, these ones took a while to go through. For the hydrologic cycle, the water cycle, we know that water is part of all of the cycles, and water is in all three states in the atmosphere. It goes up into the atmosphere through evaporation and transpiration, comes down through precipitation. I think this is all stuff we've probably heard before. The carbon cycle has slow and fast aspects to its cycle. For the fast cycling, things like photosynthesis, things like combustion, so burning, things like cellular respiration, they're all part of fast cycling. For slow cycling, things buried deep underground, things like oil, coal, rocks that are rich in carbon, some rocks like limestone are very rich in carbon, are held, they hold that carbon for hundreds, thousands, millions of years. But in the fast cycle, these things happen in a much shorter time span. The nitrogen and the sulfur cycles both had two things in common, and the major feature there that was important to remember was that there needed to be help, so a bacterial interface. There needed to be some bacteria that convert inorganic sulfur or nitrogen, so things like N2 or S8, into organic forms. Things like NH4 or NO3, or for sulfur, things like sulfates. Without the bacteria's help, we don't get enough of these into our ecosystems. The phosphorus cycle is the one that did not enter the atmosphere. Phosphorus, we're just looking at phosphates. And for phosphates, there was no atmospheric part to the cycle, just weathering, erosion, dissolving in water, taken up by roots of plants, eaten by animals, and then recycling by decomposers. We talked about the fast and slow cycling of carbon just now. Carbon enters and leaves the atmosphere mostly through combustion or cellular respiration, and it leaves the atmosphere mostly through photosynthesis. Okay. The greenhouse effect, if we have here is the Earth and here is the atmosphere of the Earth. Sunlight coming in, some of it bounces off there, that's not part of the greenhouse effect. But some of the sunlight that goes into the atmosphere is going to bounce off the surface of the Earth. At this point, it might go back away into space, but depending on the mixture of gases in the atmosphere, it has a higher or lower chance of bouncing back down again and having another chance of being absorbed by the Earth. The more times that that light is able to bounce up and down, the more likely it is to warm the planet. And that is an effect of which gases are in the atmosphere. So greenhouse gases are things like, we heard a lot about CO2. Methane or natural gas is an important greenhouse gas. Water is an important one, mostly because we have so much water in the atmosphere. Okay. For the nitrogen cycle, remember, for nitrogen fixation, there was nitrogen fixing bacteria. For nitrification, there were nitrifying bacteria. For denitrification, which is turning back into N2, that again was done by denitrifying bacteria. Most of the tricky chemical processes in the nitrogen cycle are done by bacteria. Most nitrogen is in the form of N2. Usable nitrogen is in the form of usually a nitrate. That's what we like the best as animals. For the phosphorus cycle, we said the phosphorus is usually a limiting nutrient, which means there's not that much of it, and when it gets used up, it limits the population. If you need phosphorus to do your stuff, to be alive, to grow bones and whatever, make ATP, if you don't have enough of it, then you just can't have that many humans, deer, plant, whatever is living in that area. If there was too much, that was the example of eutrophication. So again, this doesn't just happen with phosphorus, but any substance that you suddenly have too much of. And eutrophication is the example we talked about here, are blooms of algae, sudden growth of lots of algae, which cover the surfaces of lakes, creating shade below, which means that the plants and the fish that are down there are not going to have enough oxygen. Normally the oxygen comes from photosynthesis done by the plants that are on the bottom, but if the sunlight can't get down to them, then those plants cannot do photosynthesis. In the sulfur cycle, atmospheric sulfur is usually in the form of a sulfate. Sulfur enters the atmosphere usually by combustion, usually we're burning coal. And sulfate, if we mix it with water, we usually get sulfuric acid. Okay. So for energy and matter, they're different. Energy is coming from mostly the sun. Matter is coming from, well, it's all around us. It's in the ground, it's in the soil, it's in the rocks, in the whatever. Energy is something that is not 100% conserved between one level and the next. So most of it is dissipated as heat, small amounts of heat that are not useful. But almost all of the matter that we need gets recycled. For energy and matter, they both move between, so that's for both of these guys, energy and matter, they both move between trophic levels in the form of chemicals. Here, on the energy side, it's in the chemical bonds, and here it's just in the atoms themselves, the atoms and the molecules themselves. For energy, how much is recycled? Pretty much none. For matter, pretty much 100%. Which systems are closed? A closed system is a system with no more inputs. This is an open system. An open system means that there is constantly an influx of energy. So the total amount of energy in the system is not fixed, but depends on, largely, sunlight. For matter, it is pretty much a closed system, which means that the amount of sulfur, the amount of nitrogen, the amount of carbon, the amount of whatever we're talking about is the same today as it was 1,000,000 or 1,000,000,000 years ago. Slight changes because there's little bits of dust that escape to space. Sometimes rocks hit the earth and we get a little bit more iron or a little bit more silicone or whatever. But pretty much the levels of matter that we have on the earth were set about 4.5 billion years ago. We talked about the properties of water. We said that it's a universal solvent, although the word universal is misleading. It's just really good at dissolving stuff, especially things that are charged or things that are polar. We said water is really good at sticking to itself and really good at sticking to other things. We said it took a lot of energy to raise the temperature of water compared to other things. If you have a gram of water or a gram of air or steel or, I don't know, diamond, raising the temperature of water is much harder. It takes a lot more heat to put in, which helps to keep temperatures more calm, more regulated near bodies of water, and makes them fluctuate more wildly in things like deserts. Water is most dense at 4 degrees Celsius, and also ice floats. And this was a very important thing because it keeps liquid water available at the bottom of deep lakes throughout years, throughout seasons, throughout centuries, so that life can persist on the earth. In the ancient earth, we had very little oxygen and lots of CO2. This changed because of the invention of photosynthesis by our good friends, the cyanobacteria, or the blue-green algae as we call them now. And they are not everybody's good friends. Most of the things that they were alive at the time were killed off by the sudden increase in oxygen levels in the planet. And by sudden, I mean it took like 1,000,000 years. But that's pretty sudden for a change in the atmosphere. We talked about the Gaia Hypothesis, which was the concept that all of the aspects of our biosphere can be interrelated, can be trying to maintain homeostasis. Mostly it's a really good idea to think about the Earth systems as all being connected to each other. Okay. For carbon sinks and sources, a carbon sink could be the ocean is a great carbon sink. CO2 dissolves in water. Limestone is a good carbon sink. A tree that you don't burn is a good carbon sink. Lots of things that have lots of carbon dissolved in them, things like the sediment at the ocean floor, things like oil and gas reserves are good carbon sinks. Carbon sources could be anything high in carbon that is either alive, so that does cellular respiration, or anything rich in carbon that burns. Burn a tree, burn some oil, burn some gas, whatever, suddenly that carbon becomes a source. It enters the atmosphere. So source means coming into atmosphere and mixing into the air, and sink means hiding away, becoming like a reservoir. Okay. Problems in the biogeochemical cycles, the greenhouse effect. If this increases too much, so if the greenhouse effect is higher, then the planet warms. And if it's too low, the planet cools. Right now, the current risk is definitely this one. For eutrophication, we said that those blooms of algae, that's not how you spell algae, those blooms of algae, shading the water and killing off the plant life at the bottom. Aquatic life can decrease the oxygen levels available in that water. For acid rain, the effect is just, well, change in pH. And we know that for pH, this is an important factor to keep steady for enzymes to function properly, and all living things depend on enzymes. When we looked at aquatic food webs, we looked at the phytoplankton. Phyto means like a plant. And phytoplankton are floaty. Plankton means like floaty in the water, and phyto means like a plant. So they're floaty things that do photosynthesis. Zooplankton are like an animal, so they are consumers. Shrimp and salmon made it onto here because one time somebody asked me what shrimp were and what salmon were. If you don't know what they are, you're already on the internet. Go look it up. Okay. For biotic and abiotic components of ecosystems, biotic components could be things like, I'm going to write down shrimp and salmon now because I've got them on my mind. They could be things that are animals. They could be things that are algae. They could be things like invertebrates, or things like water striders, or things like whales, or anything that's alive. Abiotic components in an aquatic system, same as anywhere. Light, heat, water, and other chemical nutrients, things like sulfur, sulfates, phosphates, like sulfates, like nitrates, those types of things. So these will be the same type abiotic things as we'll find in a terrestrial ecosystem. In a terrestrial ecosystem, the living things could be, I don't know, a cow and some grass and a tree. It could be whatever three things you see that are alive. It could be a crab, it could be a beetle, it could be a mosquito, any three things that are alive on the land. I'm going to stop this quick review now. It just was supposed to be a quick reminder of what we talked about in this unit.